All right, we'll get started with this week's talk. Yang Tai is visiting from Yale, and he will tell us about learning in games.
Yep, that's right. Thanks, Matt. So it's a great pleasure to be here. Thanks for inviting me. Today I would like to talk about Last-Iterate convergence in two-player zero-sum games, or equivalently in min-max optimization. So I would like to talk about two classical algorithms, extragradient method and optimistic gradient method. I'll define them. So we show tight Last-Iterate convergence for these two algorithms. And the way we proved it is actually use sum of squares programming. All right, so. Okay. What's the best?
And also, I think you should just drag the lines.
Say again?
Like that one. You can drag that too.
Talking? This one?
Yeah.
Okay.
That's good.
Okay. All right, so I think for this audience, probably everyone's familiar with two-player zero-sum games, but nevertheless, let me still define it. So say me and Matt are playing some zero-sum game. I would choose little x from the set of feasible strategies for me. Matt would choose little y from the set of feasible strategies for him. The payoff for me is minus L of xy, and Matt's payoff is just L xy. And for today's talk, I would like to think about L as a continuous function. And for most of the talk, I'll think about a case where L is convex in x and concave in y. But in the end, I think I'll talk a little bit about the case when L is non-convex-nonconcave. And for the very familiar case, when the game is finite, you can simply write Rxy as a bilinear form using the payoff matrix. Okay, so I think two-player zero-sum game plays a really central role in game theory. So I would like to just quote Robert Aumann, who said that two-player zero-sum games are one of the few areas in game theory, and indeed in social sciences, where you can make a really unique and sharp prediction about what's going to happen. So I think to me at least, there are two reasons why two-player zero-sum games are so special. The first one is because von Neumann's seminal min-max theorem, where he showed that min-max equals max mean if you have a convex-concave function L, which turns out to imply that the set of equilibria in zero-sum games is just the same as the solution of the min-max optimization problem. And also implies that although maybe there are multiple equilibria, the payoff at any equilibria is the same. Okay. And so that's one important reason. The second one I would say is that by now we know a lot of very natural dynamics or very simple algorithms that the agents can run. And over time, over repeated play, by using these very simple algorithms, they learn to play the equilibrium. Okay. So one type of statement would be that, say, maybe me and Matt are both running some kind of online learning algorithm, and there are no regrets. For example, you can imagine we're both just running some online gradient descent algorithm to update our strategies. And then these classical results that our strategies will converge to an equilibrium. Okay. So that kind of gives another justification why you expect people to play equilibrium if there's a two-player zero-sum game. So for today's talk, I would really like to think about what these results mean by converge. As you can see, I put them in quotes. In particular, like if I run online gradient descent, does the equilibrium really converge? Okay. So here's a very simple example. So the loss function is just x times y. And I'm not even adding any constraints. Okay, so you can take any real number as x, any real number as y. And so if you think about it a little bit, the only equilibrium for this case is when you set both x and y to be 0. Okay, so that's the only saddle point of this min-max optimization problem. And I'm going to run gradient descent on the x strategy, gradient descent on the y strategy. Okay, just because x wants to minimize, y wants to maximize. Okay, so I start my algorithm at the purple point. And as you can see, this is a trajectory I'm plotting. The trajectory actually gets further and further away from the. It's not converging. Okay. Yes. So you can actually prove this quite easily for any step size. This is still the case. Right. So step size is not the issue. And so gradient descent ascent, many of you know that it's a special case of this family of no regret learning algorithms known as follow the regularized leader. So it turns out this is something quite general, this phenomenon, this diverging phenomenon is quite general. If you take a two-player zero-sum game that has an interior equilibrium, okay, and you run one of these algorithms, then this kind of oscillation almost always happens. So you can prove that, okay? When I say almost always, because if you start at the equilibrium, of course, it's not going to go away. But you know, there's a measure zero set where you start there, you would converge. Otherwise, you have the oscillation. Okay, so this seems to contradict with what I was showing you in the previous slide, right? I said classical results show things converge. So it turns out what these classical results actually prove, it's a fairly weak notion of convergence. So what they show is that if you take the average of the iterates, it does converge to the equilibrium. And that is consistent with the example. Okay. Because you're cycling around, you take the average, you will get the set. Okay. But this is a really weak sense of convergence. And if I follow the same logic, I could say the moon is converging to the Earth, which, okay, so that's sort of very weak sense of convergence. And so what I would like to understand today is, are there, variants of gradient descent ascent, very simple learning dynamics, that will have last-iterate convergence, okay? So the final one will converge to an equilibrium. I'll make this a bit more formal, just so that I cannot cheat, in the sense that I cannot just say, hey, run the algorithm, but in the last iterate, I'll be average. Okay, so I'll make this a bit more formal. So the motivation is really that I want to understand whether the whole system will stabilize. Okay, and the last iterate is the right description. Yeah. Very good question. I think the next slide will talk a little bit about it. So in the convex-concave case, no. But if you go to non-convex-nonconcave, it doesn't really make sense to take the average because the guarantees no longer hold, right? You need Jensen. So there really you want to understand the last iterate. So here we're also developing tools to understand the sets. Yeah. Correct. I don't see why we will automatically converge in the last iterate sense, but you're saying the result I will show today is good. I'm sorry, in the non-convex-nonconcave also? No. Yeah. I agree. Yes, but I think you still need to. I don't think you can do it in the last iterate. I think you still only need the averaging. But if you can use what I will show you today, I think you would get a lot. All right. Okay, right. So that's the motivation from game theory. So I would like to also talk a little bit about some motivation from optimization, maybe applications from ML. So there's a lot of I would say modern applications of ML where you can basically reduce the problem to solving a min-max optimization. So for example, you want to maybe do these deep generative models. For example, you want to generate these images of fixed celebrities. So roughly speaking, what you want to do is you want to come up with some deep neural net where the input is some boring randomness, say Gaussian, standard Gaussian. And then you want to pass it through the neural net and get a sample from some very interesting distribution. And one way to do this is through what's known as the generative adversarial networks, GANs. I'm showing you one particular way to formulate this problem. The exact definition doesn't matter that much for this talk. So the point is, you can set up with a two-player zero-sum game where there's another player, which is also a neural net. So the other player is called the discriminator, and the discriminator's goal is to distinguish whether a sample is from the real distribution or from the generator. Okay, and the generator is trying to fool the discriminator. So you can set up this two-player zero-sum game, or here really it's a min-max optimization problem. If you solved it, you should hope that the neural net you get out of this will actually give you interesting distributions. Okay, and I should say that here the loss function is usually non-convex and non-concave. All right, and so at least in the beginning, I think people were training these GANs using just gradient descent and ascent. And here's a sort of toy task where you just train not to generate this like images, but just try to get the Gaussian mixture. Okay. And this is what the experiments show. So this is what happens in the beginning, 5,000 steps, 10,000 steps, and so on and so forth. So as you can see, the algorithm never discovered the mixture. They sort of discover, single Gaussians in this mixture, and sort of, oscillates through them, but doesn't really discover the whole mixture. And maybe if you look at this, it seems like maybe the average of these outputs could be that mixture. But averaging the output is different from averaging the weights of the neural net. It doesn't mean that averaging the weights of the neural net, you will actually get that. So there's really no guarantee what will happen if you try to do the averaging trick. If you take the Last-Iterate, clearly it's not stable. Okay. So there's also some motivation here to understand whether you can stabilize the training of GANs. Okay, so that's a second motivation for understanding the Last-Iterate convergence. All right. Okay, so here is a bit more formal definition of what I mean by Last-Iterate convergence. So what I want is to figure out a function f so that for any accuracy epsilon you want, and I can tell you that as long as you run the algorithm for more than that number of steps, you would get an epsilon equation. So that's my definition. Okay, so just to avoid that, this kind of cheating, saying that, hey, I'm just going to output the average iterate in the end. Okay. So I already mentioned the game theoretic motivation. Also touch a little bit about optimization and machine learning. Really, the average iterate doesn't make sense, and we don't really have tools to understand the average iterate because you usually use Jensen. So might as well just try to understand the last. Okay, so and in the end, I'll show you a little bit that so the tools we develop for the convex-concave case will also help us analyze some algorithm in the non-convex-nonconcave. Okay, so let me move on. And so what I would like to do now is to show you actually what went wrong in the gradient descent ascent algorithm, and also show you that a sort of very simple principal way to change the algorithm. Okay, so if you run gradient descent ascent, in fact, if you can run it in the continuous time, so it turns out the continuous time dynamics will give you a trajectory that's just a perfect circle around the center. If you run it on the example I show you, where L is just x times y. But the gradient, of course, is tangent to the trajectory. Okay. So now, if you do gradient descent ascent, which roughly means you're discretizing this continuous dynamics, the gradient is still tangent to the trajectory, but now you're not taking just an infinitesimal step. You're actually taking some step with size eta. So the gradient actually pushes you out. Okay, and that happens every step, and that's why you're seeing this behavior where you're spiraling up. Okay, so a natural idea is like, okay, so we kind of understand why the algorithm diverges. Maybe there's some way you can try to correct this dynamics. And here I'm showing you one particular way to do that. Okay, so this is a classical algorithm by Popov. So what it does is I'm going to subtract 2 times the current gradient. I'm going to add back the gradient from the previous step. Okay. So why am I doing this? Why is this helpful? So let's just look at the same picture again. Okay. So say I'm at the blue point. And I'm not just going to follow the gradient. I'm going to do this kind of update. Okay. So I'm going to take 2 of the current gradient. I'm going to subtract the gradient from the previous step, which is the purple one. So I'll get this orange direction. Okay. And just from the picture, I think it kind of suggests that this does help correcting the dynamics, right? So now I'm shifting towards the equilibrium. Okay, and that's one of the algorithms I will show you a while more. Okay. And so just to say a few words about why it's called the optimistic gradient. So for the audience who are familiar with online learning, so this turns out to be just a special case of what's known as the predictive or optimistic mirror descent. And so what it does is that if you look at the difference of the t+1 iterate and the first iterate, it's basically you're adding up all the gradients, okay, except you're putting a recency bias at the gradient from just the previous round. Okay, so you're adding this recency bias. If you're just doing gradient descent, you don't have to prove. It's just you add up the gradient. Okay, so why is this recency bias called, predictive or optimistic? Well, it turns out the reason is that really what you want is you want to know what's the gradient for today, which you haven't played yet. Okay, so that of course is information you won't have. Okay, but what this is doing is like I'm gonna hope what I see yesterday will be a good prediction of what's going to happen today. Okay, so that's the optimism, and so that's this algorithm. And you can prove this is also no regret, although I'm making this sort of funny change to the update. It's still no regret. So anything people know about no regret learning algorithm will still be true for this. But I will show you that this algorithm actually has an additional property, that is, it will stabilize the whole game quickly. Okay. And I should say that so this optimism, or like adding recency bias, is a trick that people do use in practice. So people try to add this to their algorithm, and at least empirically, it seems this will stabilize the train. All right. So there's another algorithm very similar to optimistic gradient descent. I also like to talk about. And since I want to, apply the result to games, the update rule I show you in the previous slide has no projection, right? Because this is just unconstrained. If you do it on games and you do this gradient update, well, you need to do projection. So I'm just going to show you what it looks like when you do projection. So this is called the extragradient method, and I'll show you, how this relates to the optimistic gradient. So this is an even more classical algorithm by Korpelevich, and arguably the first algorithm that people come up with to solve this kind of a optimization problem. So what it does, okay, yeah, so right, I'm introducing some new notation here. So I don't want to write xy anymore, so I'm going to concatenate xy together using z to denote that. And capital Z will be the set of feasible join strategies. We use f of z, this operator, to denote the gradient for the two players. And pi of z is just the Euclidean projection. Okay, so so what does one iterate of the extragradient method look like? So I start as zt, I take a gradient step, I project it back to the set. Okay. Now I look at the gradient at this new point, this half point. Okay, and I update zt using this gradient at the half point, and then project it back. Okay, so that's my zt plus 1. And the reason I'm doing this, half point, is again, I really want to know is the gradient at zt plus 1, which I can't figure out. So I'm going to use this half point as an approximation. Okay. And so the optimistic gradient method that I showed you earlier, now, because the projection looks a bit different, but you can easily see how it relates to the extragradient method. The only difference is in the first step, I'm not using the gradient as step t, I'm using the gradient at the previous half. So I can reuse the gradient. I don't need to query gradient plus. Okay, so that's the optimistic gradient. All right. Okay, so let me tell you a bit about what do people know about these algorithms. So even in the very classical original paper that proposed these methods, people already know these algorithms would converge asymptotically. Okay, so in the limit, they do converge. But what about rates? Okay. So partially because these application scans, a lot of people start to look at this problem. In the unconstrained setting, so I would say it's quite well understood. People get high rates for both algorithms. But if you have constraints, so more like in the game theory setting, it's mostly unclear. So people have some results, but what's not known is whether you can get this type of convergence rate. The polynomial in 1/t, which is common, but also in the dimension. Okay. So there are results that have exponential dependent on dimension. So what I would like to show you is that how to get to solve this open problem. So we showed that you can run both EG and OG with constant step size. You will get Last-Iterate convergence, and the rate is polynomial in the dimension divided by root. Okay, and it works for any constraints. So one more definition just to tell you that how I'm measuring the quality of a solution. So the way I'm going to measure the quality of a solution is use something called a duality gap. In a two-player zero-sum game, it's very easy to understand. So if I have x, y, that's the strategy profile. Think about the following. So fix x, I let y deviate and see how much gain that player can have. Okay. And also I fix y, I let x deviate and see how much gain this x player can have. I add these two gains together. That's the duality gap. Okay. Clearly that's not negative. And you get equilibrium if and only if that's zero. Okay. So that's how I measure the quality of a solution. So what we show with my student Argyris and Weiqiang, we show that so you can take any z that's a compact convex set. You take this operator f, which is just the concatenation of the gradients. If f is out Lipschitz, so in the bilinear game case, that just means you have an upper bound on the payoff. Okay? And you can take any constant c, and you run EG or OG with step size that's c over L. You can prove the duality gap will decrease at this rate. D squared times L over square root of t. So d is the diameter of z, so you usually have this kind of dependence. And this is tight with respect to all the parameters I'm showing you. So matches the lower bound that these guys prove. And just want to mention that although I started in talk saying, mean max optimization, two-player zero-sum games, this result does hold for a class of multiplayer monotone games. Sorry, for all multiplayer monotone games. So I won't define what's a monotone game, but includes some interesting multiplayer games that people have studied in the literature. Okay.
Sorry, was that multiplayer game definition? Does this capture some class of dynamics?
The game? This? No, it doesn't tell you anything about how you solve it. It's just about the payoffs. Yeah.
And a little before that, that's saying this specific algorithm is type.
Yes, so this statement is for these two algorithms. Although this is also typed for a family of algorithms. The family is a bit hard to define, but you should think about it as that you have a fixed learning rate. You're doing some first order gradient method, but you have a fixed learning rate. Yeah, so maybe this is actually a good time to pause for questions. So that's the result, because starting from now on, I'll go to the analysis. All right. So I'm going to tell you a bit about the approach we use to prove these results, and also show you a sketch of the proof. Okay, so in general, the strategy that I guess everyone's using is first you establish something called a Last-Iterate convergence. You say, hey, if I run this algorithm for capital T many steps, one of the iterates. Okay, this turns out to be okay. Let me also show you. This turns out to be something not hard to prove. You can basically adapt the original analysis, the asymptotic analysis, to get this claim. So here I'm not writing duality gap, which I introduced you on the previous slide. I'm writing some other things. So I'm not going to define this for general set yet, but in the unconstrained case, this is exactly the norm of the gradient. Okay. So, and as you can imagine, if the norm of the gradient is small, I mean, your algorithm is not moving. Okay, so that should also be another way to think about convergence. And this is something that's not hard to prove, either in constraint or unconstrained. You can say the norm of gradient is the best one is of this scale. Okay, so if you also know this quantity is not increasing over time, then oh, great. The best iterate has to be the last one, right? So then you have the last iterate convergence as well. But the problem is this turns out to be pretty hard. Okay. So although you know there is one that's good, but maybe this function doesn't behave in a nice way, it fluctuates a little bit. So you actually don't know what happens in the last iterate. And I should say this is the case even in unconstrained setting. And the first paper that got this result, I think they got the rate in the last iterate sense after 5 pages of calculation, but they still need some additional assumption. So what I would like to show you in the next slide is a simple proof in the unconstrained case that shows you that this quantity is indeed non-increasing. Okay, I'm going to analyze this for the extragradient method. And I'm going to fit all the details into one slide. All right, okay, so you can take any step size between 0 and 1 of L. The claim is the gradient norm is non-increasing. When should I stop? I should stop at 120. Oh, okay. I can go on for even longer, but all right, so let me parse this into two inequalities for you. Okay, so the first one is usually called monotonicity, but if you have a if L is bilinear, so you have a finite two-player zero-sum game, this is actually exactly 0. You can verify quite easily, but not 100. If you have a convex-concave case, this is less. So I'm just using convex. Okay. Oh yeah, so capital F is the x player's gradient concatenate with minus of the y player's gradient. So if you're in the bilinear case, things perfectly cancel out, get 0. And if you're convex-concave, you just use the first order condition, you will get this. And also, if you think about this, this is like f is a gradient of a convex function. This is exactly convex. All right. And the second one, I'm just using the fact that this f operator is Lipschitz. Okay. And now I'm going to use something about the algorithm. Okay, so far this is only about properties about the operator. So now I'm going to use something about the algorithm. So I'm going to just change zk minus zk plus 1 using this update rule. So it's just eta times f of zk plus 1/2. Also, I'm going to do something similar here. I'm going to change this term using something about the operator. Okay, nothing fancy. I'm just going to rewrite this. Okay. Here I'm just throwing out the eta. Here I'm using the fact that eta is below between 0 and 1 over L. So I can replace it with L, or with 1. Okay. So I'm going to call these two terms term A and term B. And so now I want to understand, I want to prove that this h function, or the gradient norm, is non-increasing. Okay? So I'm just going to square those terms and look at the square norm of the gradient, 2 steps. So I want to prove this is greater or equal than 0. How do I do it? Well, I mean, I can clearly add A to it, because this is non-positive. I can add B to it as well. Okay. So in particular, I'm adding 2 times a plus b. Okay. This is exactly 0. Everything cancels out. I'm not using anything else. This is exactly 0. I'm just expanding this so you can verify if you like. You get exactly 0. So that's the proof. I'm adding some non-negative, non-positive terms, and I got exactly. Okay, so pretty simple proof. I wouldn't say it's very simple to come up with. And so what I would like to do next is to give you an approach that will allow you to discover proofs. Okay. Okay, so I want to talk a little bit about how to discover such a proof, and in fact, that is how we discovered this one. So what I would like to do is think about this difference of the potential function that we care about as a polynomial of what? Okay. So I'm going to write xl as the L's coordinate of a vector x. So I'm looking at all the iterates. So I mean, I only have 3 because I'm looking at this in one step, and also their gradients. So there are 6 vectors, each with n variables. So it's these are both polynomials over 6 n variables. And the goal is that I want to prove this polynomial, which is difference of these 2 gradient norms, is non-negative. Of course, there's some constraints that these variables need to satisfy, just because these things come from an algorithm. Okay. And so what are the constraints? The first constraint is this monotonicity constraint I wrote, which comes from the fact that f comes from a convex-concave objective function. Second one is Lipschitz. The last one is the update rule of the algorithm. Okay. And so my goal is I want to prove some polynomials non-negative over another set that's defined by polynomials. Okay. So I would like to take a little detour to talk about how you can do this in general, and we have some experts on sum of squares here. Okay. And so the question I want to ask is how do you certify non-negativity of some polynomial? And suppose maybe this polynomial there's also a constraint set, whether where you can take values. Okay. So target polynomial is P, and X can only take values from this set W, where it's defined by a bunch of polynomial constraints. Okay. So how can we certify the non-negativity of Px over this? Okay. So a key concept here is the sum of squares polynomial. And if you say a polynomial is a sum of squares polynomial, well, it just means that you can write it as the sum of square of polynomials, as the name suggests. And of course, if you can write P of x as a SOS polynomial, clearly it's non-negative. Okay? You don't even need the constraint set. But of course, you have constraints, you might as well use them. So here's one sort of easy certificate you can provide, which is say, hey, I'm going to be able to write Px in this form, which sum non-negative real numbers, multiply some of the positive constraints, plus some arbitrary linear combination of the constraints that equals 0, plus the sum of squares. Okay, if I can find such a certificate, I also prove to you P of x has to be negative. Okay, and by the way, this is what I show you in the proof. Okay, but you can come up with more sophisticated certificates. For example, you can replace this phi with an arbitrary polynomial. You can replace this sigma with some sum of squares polynomial. Okay, so that also is proof. But you can also go for things that are even more complicated. Maybe you can have a sum of square polynomial multiply the product of a bunch of the non-negative ones, that's also okay. But the cool thing is that there is actually a necessary and sufficient condition that people proved. That is basically you will have a certificate, not exactly this form, but some slight generalization of that. If and only if Px is really non-negative over this set. Okay, so this is some deep result from algebraic geometry. I'm just going to simply use this. Okay, and so what I hope is, okay, for me, I really have a particular polynomial that I want to prove that's non-negative, which is my potential function, the difference of the potential function, and also know some constraints. Okay, so how do we find such a certificate? So this is not something you can solve in general. Okay, so general is an intractable problem. The main difficulty is you don't know what's the max degree. Okay, so here the maximum degree of polynomial you could use could actually be very high, and there's no generic bounds on how big that needs to be. But if you decide that I only want to find certificates with a maximum degree of 2D, this turns out to be something that you can actually solve. Okay, this is you can solve this using what's known as the sum of squares programming of a particular degree, and the running time is roughly, I think I'm missing some polynomial here, but some polynomial of this thing. Okay, n is the number of inequality constraints. D is the maximum degree you want to go. Little n is the dimension. Okay. All right. And so that's actually what we did. So we solved some squares programming. In the original proof, we used some degree 8 SOS programs, and we found some certificate of this sort. Later, we managed to bring it down to degree 2. Okay, so that's roughly the general idea. Okay, so I'm about to show you the sketch of the proof in the constraint case. But there's one more thing that I need to tell you before I go there. That is, how do I actually define this potential function? So in the unconstrained case, I said it's the norm of the gradient. But that's not the right notion if you have constraints. It's very easy to see because even when your algorithm terminates or converges, maybe the norm of the gradient is still big just because you hit the boundary. Okay? So you convert doesn't mean in general the norm of gradient is small. So you need to take the constraint into account. And so this is a modification of the norm of the gradient. And here's how we take into account the constraints. So we say we're allowed you to basically subtract any vector out of the normal cone at the particular position z. So the normal cone is just all the directions where that point is the extreme point. Okay, among the set z. So if you're in the interior of the set, the normal cone only contains the all zero vector. So in that case, you cannot take anything out. So this notion is exactly the normal gradient. But if you're actually at the boundary, for example, here, so the right thing to do is you project it to the normal cone. So these are all the directions where this is the extreme point. You project this vector to the normal cone and subtract that. So the orange will be the right vector to measure. Okay. And so I should say this is a stronger notion, stronger than the duality gap. So if you know this is small, you can prove the duality gap is also small. You only need to scale by the diameter. And also, you might be wondering why I need to come up with this kind of different measure of performance or different potential function. Why can't I just use the duality gap to measure progress? Well, it turns out we run a bunch of experiments to actually get this not monotone. A lot of other things are not monotone, so you cannot really use it as a potential function to support analysis. And this is the one that we found empirically that is monotone and actually makes sense. Okay, but just to sum up, so if you prove convergence in this measure, you get convergence in all the other measures. All right, so okay, so how do you actually use the SOS? So in the unconstrained case, I think it's pretty clear, but in the constrained case, I think it's still a little subtle. So here's a naive approach to do it. So you say, hey, I have a constraint set Z. Let me use SOS. So I can write down all the constraints of Z. I try to solve the SOS. If you remember, when I show you the SOS program, the size of it depends on the number of constraints you have. Okay. So even if you can solve this, so first of all, you have to solve this for every Z because you might have different constraints. Even if you can solve this, although this is very, very large, you only get the proof for that specific Z. Okay? You're not going to get a proof for arbitrary sets. And so here's what we did. So we actually first did some reduction. So we showed that the hardest instance for the potential function that we care about actually lives in a constant dimension space. And the set, the constraint set, also only has constant number of constraints. Okay. So because of this reduction, now I only need to solve a SOS program of a constant size. And that will give you a proof for all feasible sets. Okay, just because I solve it for the hardest. Okay. And the fundamental reason that I can do such a reduction is because the algorithm that I'm looking at, the extragradient method, or optimistic gradient method, these are very simple and low dimensional. In the sense, in every iterate, I'm just doing a constant number of projections and other operations. Okay. So the way that to think about what is this hardest instance is that maybe forget about the set Z, forget about the constraint set Z for now. Just use the information, the algorithm. Okay, the algorithm tells you ZK is here, ZK plus 1/2 is there, ZK plus 1 is somewhere else. Just use this information to deduce all the constraints you can come up with. Okay, and those constraints will give you the hardest set. Okay, so let me show you what's this slide. Okay, suppose maybe I tell you, these are the 3 points in one iteration. So I start with ZK. I go there, okay, but ZK plus 1/2 is here. So no, this is a projection set. And that also tells me the set Z needs to lie on this side of this 2 hyperplane. Okay, and then ZK goes here by taking the gradient at the half step. And I also learned this green hyperplane. Okay. Also that, to write this tangent residual, I need to know what is the C from the normal comb that I should subtract from. Okay, maybe I also tell you that. Okay. So at ZK, this is the CK you should subtract from. Okay. So what I learned here, I learned some other things too, but the one thing I learned here is that this must be in the normal cone. That means the set Z must lie on this side of the blue hyperplane, the red hyperplane. Okay, so I can do the same thing as ZK plus 1. So now I learned 4 hyperplanes. And maybe the true Z is not the intersection of these 4 hyperplanes. Maybe there are other constraints. But for all I know, the set Z could really just be the intersection of these 4 hyperplanes. Okay, so if I want to prove a result, I better not use any additional constraints. Okay, so that's what I mean by the hardest instance is really actually just constant. So I should just use the ones I learned. rather than true one.
Program like depend on.
I'm not using the function. So the whole program will involve all the z's, all their gradients, all the f's, and then a bunch of inequalities between them. And those inequalities are coming from the fact that the definition I used to create is that. Okay.
Slightly higher level, like, are you saying that in your proof you find a single program that constant form blah, the whole thing is
Yes.
you solve it?
If I solve that, that works for any set.
I still don't understand the slide, but that's fine.
I have the whole proof in the next slide too. Okay, so that's again the just the potential function I want to analyze, and here are a bunch of constraints that are true just from the definition. Okay, from the definition of okay, they're true because the algorithm, or because the operators are Lipschitz and monotone. So these are things that are in general true. Okay.
This is the whole program, like K doesn't mean anything.
K doesn't mean anything here. Yeah, K doesn't mean anything. It's just one step of the algorithm, right? Doesn't mean anything. And this is not the whole program. This is what the program found, but these are a bunch of inequalities that you want to put in. And so here's what you do. You multiply this by eta squared. You multiply all these inequalities by these coefficients. Okay. You add them up. That's what you get. Yes.
I think I'm basically just gonna.
Mhm.
Like, I'm not positive. So what you're saying is that inevitably, if you want to prove that something is cognitive,
Right.
and the picture you showed on the previous slide are some facts.
These are
And then eventually you are giving a proof that it is non-negative just using the facts.
Correct. Correct.
The human readable proof in the index that is really hard to come up with.
That's right. So this one I think is really human readable. The degree 8 one, arguably. So this is a fun story that in the first submission we actually included a 5-page table just to verify its identity. So left hand side is something, right hand side is something else. Right hand side is sum of square, left hand side is sum of bunch of polynomials. You can spend like 5 hours to reach the table and you can verify it, which I actually did once, but yeah, anyways, you can do it. This one is pretty easy to verify. Yeah. Yeah, so I think some of the steps are quite heuristic so far, but I will show you that so we did this for the extragradient method. I mean, there's this other method, the optimistic gradient method. Turns out we didn't. I mean, at least for us, we didn't do it. Just one more time. There, we actually managed to use SOS directly to find the potential. I don't even need to sort of guess the potential function, then putting all these constraints, and then do it. So just because I know these constraints, so some similar algorithm will also have similar constraints, and I kind of know what are the right ones to include. So for that one, you can actually. Right. Right. Okay. So that's the proof. Is you can verify if you spend some time. Right. So I was just saying this, like turns out if you look at the optimistic gradient, here's the potential function. So it's not the same. You need to add an additional term. And the way we did it is basically we say, hey, we think the potential function will have these components, and we basically just build a basis. And that is kind of heuristic. And then you just run some SOS program. I say, hey, I allow you to take any linear combination of these basis functions. Of course, you want this linear combination to be non-increasing, and also you know, you incorporate the constraint I have. And we found this potential. Yeah. So right. I think this is something you could do in general for, you know, iterative methods. Of course, you need to understand the algorithm. You need to understand what a constraint. Okay. Okay. Let me don't go over this very carefully. I just want to show you this one slide. So, so I was talking about, you know, so far I've been talking about convex-concave problems. And so the algorithm I show you gives a 1/√t convergence rate. Turns out you can use, you know, the insights from the analysis for those two algorithms to develop the optimal algorithm for this problem. So you can get 1/t convergence rate. And the modification you need to do is that on top of doing this extra gradient step, you add these two terms, which sometimes people call the anchoring or helper iteration. But it's roughly you're adding a regularizer to the payoff of the game. Okay. So this you can get 1/t convergence. The analysis is kind of inspired by what we did in those two previous algorithms. And
Sorry, how does that break the model that you said 1/√t for?
yeah, because this is time dependent.
Time, not like 0.
No, because the learning rate is not constant. You have this time dependency.
Okay.
Yeah. Right. Okay. So I don't want to go over this. So basically, that algorithm also works if you don't exactly have convex-concave problems. And so there is a family called the row comonotone operators. So I'm just going to give you one example. So here the loss function could look like that. This is actually not convex in X, it's concave in X. It's convex in Y. What you want is convex in X, concave in Y. Okay. This function is not a convex-concave problem. And you know, you can still use the algorithm I showed you in the previous slide on this, still get, you know, 1. So it does work for some non-convex-nonconcave settings. And also there is a recent hardness result showing that if you're in general, in a general non-convex-nonconcave setting, you cannot hope to find a stationary point. Okay, and that's all these algorithms are doing. You cannot hope to find a first order stationary point. That was the recent hardness result. So you need to look at sort of more structural settings, and this is okay. So let me conclude. So I guess the first takeaway message is that so there are indeed natural dynamics that will have last-iterate convergence. Key idea is you need to add optimism to the algorithm. Okay. So we analyzed sort of we'll analyze two algorithms, optimistic gradient and extra gradient. I mean, there are other versions of this optimism. You can do optimism with MW, for example. Okay, that's called optimistic hedge. We actually don't know how to analyze that. And the SOS approach, at least I don't see how exactly to adapt it to work, because the metric is not the L2 norm, it's this Brackman divergence. So I didn't figure out, or like we didn't figure out how to adapt this SOS there, but you know, we believe it's still has last-iterate convergence. Is probably also 1/√t. And also you can accelerate the algorithm to get 1/t by adding this additional term in the algorithm, right? And also I think this approach uses the SOS programming. It seems quite powerful, and I think there's potential to use this on other first order methods. Yeah, with that I'll stop and take questions. Yeah. Uh-huh. Yes. Yeah, right. I think you certainly can. We haven't tried. So one thing that initially I think it's particularly challenging for us here is you need to deal with constraints. As far as I understand, like the work by Ben Rack, and at least in their paper, they didn't deal with constraints, with the unconstrained setting. And for unconstrained setting, it's actually much easier to do it because you don't have to do this reduction, right? So all the coordinates are equivalent, are symmetric, so you just solve this quite easily. Yeah, so we haven't tried, but yeah, I think it would be interesting to try. Well, actually, I mean, if you have like algorithms like you think, we're understanding the accurate rate, I think this is the useful approach.